Today we're doing section 4.3, linearly independent sets and bases. Linearly independent. A set of vectors v1 through vp in a vector space V is said to be linearly independent if the vector equation c1 v1 c2 v2 all the way to cp vp equals 0 has only the trivial solution c1 equals 0, cp equals 0. Linearly dependent. The set of vectors is said to be linearly dependent if there exists weights c1 to cp, not all 0, such that c1 v1, c2 v2, all the way to cp vp equals the 0 vector. Recall section 1.7 for the general vector spaces. The following still hold true. First, a set contained in the 0 vector is linearly dependent. A set of two vectors is linearly dependent if and only if one is a multiple of the other. And a set contained in only the 0 vector is linearly independent. Let's look at example 1. State whether the following set is linearly independent or linearly dependent. And this set is linearly dependent because it contains the 0 vector. State whether the following set is linearly independent or linearly dependent. And this set is linearly independent. And this is because 3, 6, 9, 11 is not a multiple of 1, 2, 3, 4. Theorem 4. An index set v1, v2, all the way to vp of two or more vectors with v1 not equaling 0 is linearly dependent if and only if some vector v sub j greater than 1, is a linear combination of the preceding vectors. Let's look at example 3. Let p1, p2, p3 be the set of vectors in p2 where p1 of t equals t, p2 of t equals t squared, and p3 of t equals 4t plus 2t squared. Is this a linearly dependent set? And when you look at this, we can write p3 in terms of p1 and p2. So since p3 of t equals 4p1 plus 2p2, P1, P2, and P3 is a linearly dependent set. Let H be the plane illustrated below. Which are valid descriptions of H? So, H equals the span of V1, V2. H equals the span of V1, V3. H equals the span of V2, V3. And H equals the span of V1, V2, V3. So, only one of these is not a valid description. And the one that is not a valid description is C. So A is a valid description, B is, and D is. But C is not because V3 is a multiple of V2. Basis for H. A basis is a set of efficient span and set containing no unnecessary vectors. In this case, we would consider the linearly independent sets v1 and v2 and v1 and v3 to both be examples of basis sets, or bases, plural for basis, of 4H. Let H be a subspace of vector space V, an index set of vectors beta equals B1 all the way to BP in V is a basis of H if, first, beta is a linearly independent set, and two, H equals the span of B1 all the way to BP. So let's look at example 4. Let E1 equal 1, 0, 0, E2 be 0, 1, 0, and E3 be 0, 0, 1. Show that E1, E2, E3 is a basis for R3. So we're going to let matrix A equal E1, E2, and E3. So this would be the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Since A has 3 pivots, we have 3 pivots in A. The columns of A are linearly independent by the intermediate value theorem. And the columns of A span R3 by the intermediate value theorem. Therefore, E1, E2, E3 is a basis for R3. Let's look at example 5. Let S be 1t squared all the way to tn. Show that S is a standard basis for P of n. So what we're going to do is let C0, 1 plus C1 times t plus C2 times t squared plus Cn times t to the n equals the 0 vector times t. And you need to remember that this 0 vector is like 0 times 1, 0 times t, 0 times t to the n. So then C0 equals C1, which equals Cn, which equals 0. Hence, S is a basis for Pn. Example 6. Let V1, V2, V3 be those vectors. Is V1, V2, V3 a basis for R3? So we're first going to let A be the matrix V1, V2, V3. So that would equal 1, 2, 0, 0, 1, 1, 1, 0, 3. And using row reduction, we're going to reduce this matrix and see if we can get 3 pivot columns. If we can get 3 pivot columns, then the columns of A are linearly independent, and they would span R3. And therefore, V1, V2, V3 would be a basis for R3. So let's see if we can go ahead and do that. So 1, 2, 0, 0, 1, 1, 1, 0, 3. The first thing that I notice I can do is I can take negative 2R1 and add it to R2, and that will help me out there. And then I notice that I can take negative 1 R2 and add it to R3. So we could continue and divide this one by 5 and then also get it into our identity matrix. But we already noticed that we have 3 pivot columns here because 1, 2, 3. So since we have 3 pivot columns, the columns of A are linearly independent. And they span R3. By the Intermediate Value Theorem. Therefore, V1, V2, and V3 is a basis for R3. Let's look at example 7. Explain why each of the following sets is not a basis for R3. So we have this first set, A. So we have these 4 matrices, and why would this not be a basis for R3? So this is linearly dependent, hopefully you said. And that's because there are more vectors than there are entries per vector. So in other words, there's too many columns. Let's look at B. We have 1, 2, 3, 4, 5, 6. And if you notice this, you could also let this be A equals. And since there's not a pivot in every row of A, the columns of A do not span R3. So in order for it to do that, for you to be able to get a pivot in every column, you would need one more column. The basis for null A. Find a basis for null A where A equals this. So what we would need to do is we need to row reduce our matrix A in the 0 vector to get answers, okay? So we would have and believe it or not, it doesn't take that long to do this. So the first thing that I would do is I would take negative row 1 and add, or negative 2 row 1 and add it to row 2. So row 1 would stay the same. And I take negative 2 row 1 and add it to row 2. Then I would take 1/3 row 1. You get 1, 2, 2, 1, 3, 0. I didn't do anything to row 2. And then the last thing I would do is take negative 2 row 2 and add it to row 1. So with this, I would have x1 equaling negative 2x2 minus 13x4 minus 33x5. x2 is a free variable. x3 would equal 6x4 plus 15x5. x4 is free, and x5 is 3. So then what we could do is we would write x. I'm going to go down a little further so I have a little more room. So using this information up there, we would have x equaling x2 times negative 2, 1, 0, 0, 0, plus x4, write this in terms of the free variables, negative 13, 0, 6, 1, 0, plus x5, negative 33, 0, 15, 0, 1. So this would give me vector A, or matrix A. And one thing we would call this UVW. We would put UVW into this, and UVW is a span and set for null A. Therefore, UVW is a basis for null A. Theorem 5, the span and set theorem. So this goes with the previous one. Let S be V1 all the way to VP, be a set in V, and let H span V1 to VP. A If one of the vectors in S, say v sub k, is a linear combination of the remaining vectors in S, then the set formed by S by removing v sub k still spans H. B, if H does not equal the zero vector, some subset of S is a basis of H. So let's look at example 9. Suppose that v1, v2, and v3, and x is in the span of v1, v2, v3. Find the basis. So first, if x is in the span of v1, v2, and v3, then x equals c1 times v1 plus c2 times v2 plus c3 times v3. And then if I write this in terms of v1, v2, v3, I can rewrite v3 as 2v1 and 3v2. So I could rewrite this as c1 v1 plus c2 v2 plus c3 times 2v1 plus 3v2. And then looking at this, I can rewrite each of these and factor out a v1 and v2. So my v2s would go, I would distribute these, and then my v2s would go together and my v1s would go together. And I'd have c1 plus 2c3 equal times v1 plus c2 plus 3c3 times v2. So therefore, span of v1, v2, v3 equals the span of v1, v2. Because we started with it in terms of v1, v2, v3, and we get it down in terms of v1 and v2. Let's look at the basis for our columns. So example 10, let A equal A1, A2, A3, A4, which is that matrix. Find a basis for column A. So we're going to use elementary row operations on a matrix. Just remember they do not affect the linearly dependence relations among the columns of the matrix. Okay, so just remember that. So we're going to reduce these to see if we can prove that the span of A1, A2, A3, A4 equals the span of A1, A3 by getting it down to just 2 pivot columns. So we are going to take our matrix and we're going to row reduce this. So the first thing I'm going to do is I notice if I multiply my first row by -4 and add it to my last row, that zeroes out my last row. Next, I notice if I take -3 row 1 and row 2, I can zero out the first two. I can zero out 3 and 6. So I'm not going to do anything to row 1. I'm leaving row 2 alone. I'm going to take negative 3 row 1 and add it to row 3 and get 0, 0, 2, 10. And the last row was already zeroed out. I'm going to go on up here. The next thing I'm going to do is I'm going to take negative 2 row 1 and add it to row 2. So row 1 is still the same. Taking negative 2 row 1 and adding it to row 2. And then if I take negative 2 if I take 2 times row 2 and add it to row 3, that zeroes that out, and I can also get rid of my negatives, and then I'm down to 2 pivot columns. And we're going to say that this equals B1, B2, B3, and B4. And if you notice here, B2 equals 2B1 and A2 equals 2A1. And then if you also notice, B4 equals 4B1 plus 5B3, and A4 equals 4A1 plus 5A3. B1 and B3 are not multiples of each other, and A1 and A3 are not multiples of each other. So therefore, the span of A1, A2, A3, A4 equals the span of A1 and A3. And A1 and A3 is a basis for column A. Theorem 6. The pivot columns of a matrix A form the basis for column A, which we just did. Let's look at example 10. Let V1, V2, V3 equal those matrices. Find the basis for the span of V1, V2, V3. So we're going to let A equal 1, 2, negative 3, negative 2, negative 4, 6, 3, 6, 9. And note that the column A equals span of V1, V2, V3. Okay, so we're going to row reduce this. So the first thing I can do is I can take negative 2 row 1 and add it to row 2, and that would cancel that out to zeros. And then I notice that I can take 3 row 1 and add it to row 3. So we'll go right here. So I take 3 row 1 and add it to the row 3, and I get 0, 0. Drop my negative right there. Get 0, 0, 18. And then I can switch row 2 and row 3. And then I can divide row 2 by 18 and take -3. So let's divide row 2 by 18 first. And we'll come up here. And then I can take -3 row 2 and add it to row 1. And the basis for the span of, so now I have this here. And since I have a pivot column in row 1 and a pivot column in row 3, the basis for span V1, V2, V3 is my V1 and V2. Because I have my pivot column in row 1, so that corresponds to V1, and my pivot column in row 3, that corresponds to V3. So those are my best, that's my basis for the span of V1, V2, V3. So to review, to find the basis for null A, use elementary row operations to transform A0 to an equivalent row-reduced echelon form B0. Use the row-reduced echelon form to find the parametric form of the general solution, AX equals 0. The vectors found in the parametric form of the general solution form a basis for null A. And 2, a basis for column A is formed from the pivot columns of A. Warning, use the pivot columns of A, not the pivot columns of B, where B is the reduced echelon form and is row equivalent to A.